Alright guys, it's time to learn about homework 6. So, obviously I'm not here to walk around and see if you did it, but you need to make sure that you have attempted all of the problems before you Hey guys, welcome to the video about homework 6. Hope everything is going well in my absence. Just a thing to make sure you understand. You need to have done these problems before you watch this video. Okay? So if you have not yet attempted the homework problems, stop what you're doing. Don't just write down what I'm doing here because you're not going to get that much out of it. Attempt everything before you try and watch the video. Alright, now, going through, starting from the top. Objective question 4 is really honing in on some of the vocabulary terms related to circular motion. So when it's talking about a centripetal acceleration and a tangential acceleration at different places, just as a reminder, a centripetal acceleration is the inwards acceleration something experiences when it's moving around some portion of a circle. That means that it has to actually be moving in order to experience that inwards acceleration. All right, so that's one important thing, is that it must be moving at that point for there to be a centripetal acceleration. Tangential acceleration, and so this just causes a change in the direction. Right? That's what it changes, is the direction. All right, a tangential acceleration, though, there's no special formula for that one, but what a tangential acceleration does is it changes the speed of the object as it's moving along, again, some portion of a circle. So, for a car, the centripetal acceleration comes from the steering wheel, right? Well, friction, but you turn the steering wheel to make this happen. You hit the gas pedal to make this happen, right? So the tangential acceleration would come from the work of the engine, whereas the centripetal acceleration would come from you steering the car. All right. So if it's not moving, this is 0. If its speed is changing, then this one is not 0. So if we look at all these different spots, A wants to know, where would the centripetal acceleration be not 0? All right, well that would be anywhere where it's moving. So if it starts at A and, goes up as high as D, it's stopped at those two spots. At position B, though, it's still got a little further to fall, so the tangential acceleration is not 0 there. So that means only at position C would both of those be true. All right, centripetal acceleration is 0. All right, we can stop thinking. That's got to be A and D pretty much. All right, now, it is worth noting, though, that the tangential acceleration is not 0 at either of those spots, because if it stops there for an instant, obviously it's going to fall back down. All right, centripetal acceleration is 0, tangential no, there's nowhere where that's true, unless you just hold it right here at C and let it go. Okay, so not applicable. None of the above. Centripetal acceleration is not 0, and the tangential acceleration is not 0. Well, that would be position B, because it's still speeding up as it falls further down, and since it's moving, it has a centripetal acceleration because its velocity is changing directions, right? From moving at a downish angle to moving completely horizontal at position C. All right. Objective question 7 about this hanging iPod, whatever those are. So I'm sure that you have seen something like this, if not on an airplane, at least riding around in a car. If you've got something hanging from the rear view mirror, if you accelerate forwards, it swings back towards you. Or at least that's what it looks like it's doing. What do you mean that's what it looks like it's doing? Well, okay. Everything in the car is moving forwards, let's say, right? So you, the air freshener or whatever it is, they're all moving forwards, okay? So if this is the direction of the acceleration of the system, you guys know from experience that the iPod or whatever will swing backwards. All right, now the reason it swings backwards is in order to have a forwards acceleration. All right, and also because it has inertia, which is resistance to acceleration. So given its inertia, it's not just going to go forward with the rest of the car. It'll attempt to stay in one spot by swinging backwards. But I think the better way of thinking about this is that it actually has to swing out like that in order for the tension to be able to pull it forwards. If it were still hanging straight up and down like that, the tension would only be vertical, and there would be no horizontal component to it. And therefore, the cord would be unable to pull the iPod forward. So you actually need both an upwards component to oppose gravity and a forwards component to cause the acceleration. All right, so if I wrote some equations for the sum of the forces along each of those axes, for the y direction, it would not just be T minus mg. It wouldn't just be T minus mg because that tension is at an angle, and so therefore I have to do the vertical component. Now there's some shenanigans here with the angle theta. If you all see, it's given from the vertical, so therefore the cosine component, which is the adjacent side, would be the vertical component in this scenario. All right, so the vertical component of the tension is what holds it up, meaning is what opposes gravity. All right, so you could find the tension like that. And then for the x direction, the sine component is related to the horizontal component of the tension. And that equals, well, what does that equal, Mr. 0? No, not 0. The iPod in this scenario is not actually in equilibrium. It's accelerating that way. If it's accelerating that way, then that means that the sum of the forces is not 0, but I should hear a chorus of MA! Yes, that would be correct. MA. Okay, so what that ends up giving you, if you put those two things together, is that the angle to which it swings out corresponds to the forwards acceleration. And this does bear out in real-life experience, right? If you've got something hanging from the rearview mirror, if you accelerate a little, it swings out a little. And if you're like flooring it, then it will swing out a bit more. Okay, so the greater the acceleration it experiences, the more it's going to swing out. All right, and then conceptual question 7. If you had trouble picturing it, this is kind of the idea. The cylinder's spinning like this, and you actually saw something just like this in the movie Interstellar. Now, I'm not sure that this is exactly what the makers of that movie had in mind, because at the end they sort of learn how to manipulate gravity itself, and so maybe they're actually just creating artificial gravity inside of this cylinder or something. All right, but one way to simulate gravity, which they actually do earlier in the movie when they're in their spaceship and it starts spinning, is to spin the thing that you're on. So a guy standing on the ground here doesn't experience the force of gravity exactly. Since the rotation is like this, he would experience a centrifugal force out from the circle. And this guy on the ceiling would experience a force upwards out from the circle. And then this is one of those extremely rare circumstances where we don't throw in gravity, because the whole idea is that we have to simulate gravity. There isn't really much gravity to speak of in this scenario. All right, well, he's on the floor, so he's got a normal force upwards. This guy's on the, quote, ceiling, has a normal force downwards. Both of them are being pressed into the floor by the centrifugal force exerted by that spinning cylinder in space. All right, so it's a way of simulating gravity. Both this guy and that guy would say that they are being pushed towards the floor by that centrifugal force that they are experiencing. And so which way is down? Down is out of the cylinder. There's not exactly an up or a down to speak of, at least not in a proper sense. All right, let's see if I missed anything here. Okay, whatever. Say something about those forces and the fact that you're spinning and therefore you experience a centrifugal force and therefore you feel like there is gravity. Question 89 from chapter 5 is actually just like a problem that you guys did, it's not just like a problem that you did on the homework 2 worksheet, but it is just like one that we did in your notes packet, except that they did some funky stuff with it in terms of the symbolic answer. So the example that you ought to go look back at is example 6. Okay, so this is example 6. The only thing that I want to address here is the shenanigans that they're pulling with calling it FG for force of gravity, and where in the world secant and tangent came from. Because if you do what I did in example 6, you're going to get mu mg over cosine theta minus mu sine theta. And those don't necessarily obviously look the same. All right, so you can go back and look at the work that I did on this and figure out how that one goes. So just look at the answer key, which is posted in the drive. But where it says Fg, all right, the force of gravity is mg. So I don't know why they called it that. Secant, though. All right, if you've never heard of secant before, you might not be alone in the room not having heard of secant. Secant is 1 over cosine. So there's no reason to go from this to that. What they did was they multiplied top and bottom by 1 over cosine, also known as secant. And if you do that, what you'll have is cosine times 1 over cosine is, of course, 1. And then mu sine theta times 1 over cosine is going to give you sine over cosine is tangent. So minus mu tangent, since sine over cosine is tangent. All right, and then for the top, 1 over cosine is secant. So mu mg secant theta. All right, if you need to see more on that, then you should go look back at example 6 from your notes packet, and you can see how I worked it out symbolically, and then at the very end I plug in numbers. All right, next question. For this one, they want to know the range of possible values for the velocity that this 3 kilogram puck can have as it goes around that circle. And then seemingly unrelated to that, they tell you, oh, this same string held up a 25 kilogram weight earlier today before snapping. All right, fine. So it seems like you've got two completely unrelated pieces of information, but what they're trying to give you is, hey, look, there's a maximum tension that that string can have before it snaps. That's true for any string, right? If you pull on a string hard enough, it will probably snap, or hang something heavy enough from it, it will snap, all right? And so this is a way of giving you that information. All right, so the forces acting on the system that I've drawn to the right are where you have to begin, because you have to figure out what that maximum tension is. So weight, tension, and that right there is going to be the maximum tension. All right, if it's in equilibrium here, but like just barely, because the string's about to snap, then 0 over there, T equals mg, and the maximum tension would be whatever 25 times 9.8 is. All right. Now, over here, the forces acting on this would be, it's got tension holding it into that circular path, and it has the centrifugal force acting outwards on it. All right, and so that means if it's in equilibrium, T minus Fc equals 0, put in this maximum tension to get the maximum speed, where T max will equal mv squared over r. Now they say a range of speeds, whatever, the minimum speed is 0, and you would use that calculation there to get the maximum speed. for part 2.